Hello, everyone. Good morning to those of you who are in the morning session, I guess. Welcome to the online causal inference seminar. So today we actually have two talks, both from MIT. So this is our special MIT day. So the first talk is going to be by Rahul Singh on causal inference with corrupted data, measurement error, missing values, discretization, and differential privacy. And actually, Rahul has Anish Agarwal in the Q&A helping to answer questions. Afterwards, we have a talk by Jiaji Zhang from MIT on active learning for optimal intervention design in causal models. So we hope you enjoy both talks. And the questions today will be handled by Ying. Please feel free to submit them at any point. I will switch over now to Ying, who will explain how do you do that.
Thank you, Emma. Just as usual, please submit your questions through the Q&A section. If you haven't used it before, it is just a button at the bottom of the Zoom window. So please do submit your questions through the Q&A so that we can better track them. Without further ado, Rahul, I think you can get started.
Here we go. Is that working well?
Perfect. Yes.
Perfect. Great. Thank you. So today I'll present causal inference with corrupted data, measurement error, missing values, discretization, and differential privacy. This is joint work with Anish, who's currently at Amazon, and even more currently, he's in the chat. I'd like to begin with a headline from the New York Times. The 2020 census suggests that people live underwater. There's a reason. And that reason is differential privacy, which will be achieved by injecting synthetic noise into the dataset before it's published. Differential privacy is already widely implemented in the technology sector, for example, in the high-dimensional datasets collected by Apple iOS and Google Chrome. Only recently, it's been adopted in the government sector, in the censuses and surveys that inform policymaking. And that's led to a round of warnings that there'll be a painful trade-off between the privacy of individual respondents and the precision of policy analysis. Why does the census need privacy? Researchers at the Bureau simulated an attack on the 2010 census. So the 2010 census consists of these tabular summaries that are ostensibly anonymous with a lot of cross-tabulations. For a certain census block, how many people have characteristics A and B and C and D and so on. And these can be viewed as a system of equations and then solved to reconstruct microdata without names. Then, pretending to be hackers, we could obtain an external data set of names and addresses and try to merge the two. What did they find?
Rahul?
Yes?
Sorry to interrupt you. Is it possible to make your microphone a bit louder?
It is.
It's very clear. It's just a little bit quiet.
Sure, yeah.
Thank you.
Yeah. Play with this. Oops. I'll briefly stop sharing too.
Oh, sorry.
Is this any better?
I'm not sure, but it's perfectly clear, just a little bit quiet. So it's fine. You can continue, please. Sorry to interrupt.
Yeah, sure. I'll try to speak a little bit louder as well. Great. And so they simulated a hack, and they found that depending on the quality of the external data used, between 52 and 179 million respondents to the 2010 census could be correctly re-identified from the microdata. This finding had shockwaves at the Bureau, and it caused its leadership to really rethink how they publish the census and other data products. In addition to these tabular summaries, the Bureau publishes microdata on wages. And in the interest of privacy, the Bureau has announced that it will discretize wage data. So historically, we could use a tool like the Atlanta Fed Wage Tracker to track wages over time. And so historically, we had access to data like the Blue Series. What if we implemented this proposed rounding or discretization scheme? Well, then we'd have the Red Series. We can see it's very corrupted and even degenerate for a period of time. There was a substantial backlash, especially among economists who use this wage data, and the policy was delayed. what are the experts saying? Professor Cynthia Dwork, one of the founders of differential privacy, has reflected on the hack that we saw, saying, imagine a kind of weaponization, one where somebody decides to make a list of all the gay households across the country. I expect there will be people who would write the software to do that. Professor Charles Mansky, a leading econometrician, has reflected on the data corruption and said, this is not a minor technical issue. It's an inescapable tension between enhancing privacy and enhancing data usability. Perhaps most provocatively, Professor John A. Bowd, the chief economist of the US Census Bureau, has written in the American Economic Review, until now, our discipline has ceded one of the most important debates of the information age to computer science. What does this mean for causal inference? In this work, we'll think about this problem as a causal inference problem, that social scientists are worried about how these new types of data corruption, the differential privacy and discretization, will undermine our ability to do causal inference. Of course, even before 2020, the census had old or classical types of data corruption, which are very much studied in causal inference, like missing values and measurement error. And so we're interested in doing causal inference in the presence of both the classical issues and the modern ones. The standard workflow for doing causal inference from a real-world data set is to do some data cleaning and then to do some data analysis that typically ignores the bias and variance consequences of the data cleaning. And in this work, we'll propose a new end-to-end procedure for data cleaning, and then estimation, and then inference with data cleaning adjusted confidence intervals. Formally, we'll prove root-end consistency, Gaussian approximation, and semiparametric efficiency by finite sample arguments. And our key assumption throughout that will power everything is that the true covariates are approximately low rank. We'll argue that there exist scenarios in which it seems to be possible to achieve both privacy at the individual level and precision at the population level. In this work, we build on many that come before. In semiparametric statistics, there are classic works on the asymptotic variance of semiparametric estimators. We also build on the targeted and debiased machine learning literatures, and I'll point out the connections as we go along. There's a literature on using principal component analysis for large factor models, where the authors try to identify and infer these latent factors. We'll be interested in downstream causal parameters instead. And while a latent factor model is sufficient, it turns out to be not necessary. There's a lot of work in causal inference on doing estimation in the presence of various data corruption. So for missing values, Rubin proposes multiple imputation. And the synthetic control literature can kind of be thought along these lines, where the causal parameter of interest is the average treatment on the treated in a panel data setting and using a factor model. We'll be interested in a broad class of causal parameters, not just average treatment on the treated, in cross-sectional data, and the factor model will not be required. Finally, our work relates to various literatures on error in variable regression. In causal inference, this often means using auxiliary information like repeated measurements or instrumental variables or negative controls. And I'll try to make the case that our work continues this repeated measurement idea. In statistics, various works extend the lasso and the dancing selector to error and variable regression, but then the analyst needs to know in advance the covariance structure of the measurement error, and that's something we want to avoid. Our work relates to the literature on principal component regression, and in particular, we'll propose new variants of principal component regression for causal inference. So we're motivated by this question of how to do causal inference with the 2020 US Census, and if it's even possible with high dimensional corruptions like discretization and differential privacy. I'd like to introduce a little bit of notation. I'll denote the outcome by Y, the treatment by D, and the covariates by X. And for today, I'll talk about the average treatment effect with INID data. So the average treatment effect is theta naught, and it's the sample mean of individual treatment effects. Our interest in INID data comes from the fact that we're interested in data corruptions. And if we believe the data is corrupted, we probably believe it's not identical. In the paper, we consider a broader class of causal parameters, like the local average treatment effect and elasticity, and even non-parametric causal functions, like the conditional average treatment effect. The crux of our problem is that instead of getting to see YD and X, we see YD and Z, where Z are corruptions of X. So concretely, we can imagine for the ith observation, there are 5 covariates. That's the first row. In the presence of measurement error, we don't get to see those 5 covariates. We see those 5 covariates plus, let's say, Gaussian noise, and those are the 5 values we see instead. Or perhaps there's missingness, where instead of seeing those 5 values, we see a subset of them. Or discretization, where, for example, the 5.15 has become a 6. Or maybe there's privacy, where instead of seeing those 5 values, we see those 5 values plus, let's say, Laplacian noise. And why Laplacian noise? The idea is that if you add Laplacian noise to tabular summaries, then it provably becomes very hard to reconstruct the microdata. Differential privacy is a formal guarantee of plausible deniability that any individual contributed their data. So this is precisely the step of the simulated hack that gets disrupted. I'd like to introduce a visual language which will help us think about the algorithm and the theory. And it'll also help us understand these 2 equations, which concisely summarize our model. So we have a vector of outcomes y that are generated from a regression function that we'll call gamma naught, with an argument for treatment and an argument for the clean covariates. There's also a vector of response noise. But we don't get to see the matrix of clean covariates. Instead, what we get is a matrix of corrupted covariates. So it's the clean matrix plus some additive corruption, whether that's measurement error or discretization or differential privacy, all of which are, by the way, sub-exponential. That is to say, their tails are no worse than an exponential distribution, and that'll show up in our theory section. Then we'll multiply by a missingness mask, which corresponds to non-response. So this is how we accommodate missing values. Altogether then, we don't get to see y, d, and x, we get to see y, d, and z. Our key assumption that will power everything is that the true covariates are approximately low rank. So the matrix of clean covariates is an n by p matrix for n observations and p variables. And we're saying that it's well approximated by a matrix that has rank only r, where r is much less than n and p. And I'd like to suggest the intuition of a repeated measurement model. In the classic repeated measurement model, we have 2 noisy measurements of 1 signal. And in our model, the idea is that we have p noisy measurements, where p is an increasing number, and they're not precisely repeated measurements, but approximately so, of just r signals, where r is allowed to grow, but it's growing much more slowly than n and p. Geometrically, we can visualize this assumption. So in this plot, we have 3 covariates, x1, x2, x3. So the ambient dimension p is 3. We're visualizing n observations as n data points. And we see that they're well approximated as living on a 2-dimensional subspace. So R is 2. When visualized this way, we get another intuition that approximately, when it comes to treatment assignment, there's approximate selection on the subspace. In the paper, we keep track of what happens if there's selection that's not on the subspace, but we're making this approximation assumption. So we'll keep track of all the approximation errors with finite sample bounds. Why would we place an assumption like this? Well, because it seems to hold in census data. So here we've loaded the covariates from Otterdorn and Hansen's 2013 paper in the American Economic Review. In their 30 covariates, we've done the singular value decomposition and then visualized the singular values, also called the principal components. And we see that maybe just the first 5 principal components explain most of the variation in the data. We also see the intuition of approximate repeated measurements, because among these variables, we have average disability benefits and average medical benefits and average unemployment benefits, which are not precisely repeated measurements, but maybe approximately so. We see how reasonable this assumption is in related economic data sets. So what if we look at household level data in the PSID or CPS? Again, we see that the approximate rank, R, is much lower than the ambient dimension P. And we're able to verify this kind of property in county level data sets and commuting zone level data sets from Chetty and Hendren's influential papers in the Quarterly Journal of Economics. So the takeaway is that the census is approximately low rank because it has these approximate repeated measurements, and that'll power all of our analysis. Before I present the algorithm, let me tell you about the algorithm we want to have. We want to have an algorithm that estimates causal parameters as if the data were uncorrupted, yet adjusts for data cleaning in the confidence interval. Ideally, this procedure would not require knowledge of the corruption covariance structure in advance. And in this way, we depart from previous work and connect more to the matrix completion literature. If such a procedure were to exist, we would in some sense preempt the looming trade-off between privacy and precision. The premise of matrix completion is that you get a matrix that's n by p. There are missing values we want to fill in, and present values we want to denoise. And in this paper, we'll think of matrix completion as a type of automatic data cleaning. So when we're doing data cleaning, we're really making a matrix estimator x hat of the clean covariate matrix X. There's a vast literature on matrix completion, and our aspiration is to do this automatic data cleaning, which is very agnostic about the noise, and then adjust for the data cleaning in the confidence interval. But this is hard to do. Several challenges arise. The first challenge is that the best rates of matrix completion are actually slower than n to the minus a half. So how could we possibly do causal inference with a standard error of order n to the minus a half? And our answer will be to aim to extend double rate robustness, which motivates us to use the W robust moment. The W robust moment combines two classic formulations: that of the outcome mechanism, where the outcome mechanism is the expectation of the outcome Y given the treatment D and covariates X, and that of the treatment mechanism, where the treatment mechanism is the expectation of the treatment D given the covariates X. In the outcome mechanism formulation, the treatment effect is the outcome mechanism of treatment on minus the outcome mechanism of treatment off in expectation. And in the treatment mechanism formulation, the treatment effect is the reweighting of the outcomes by the balancing weight, which has the treatment mechanism in the denominator. In this work, we'll propose new error invariable estimators for this regression and this balancing weight. And in particular, having an error invariable balancing weight seems to be a straightforward idea, but actually a new idea. The second challenge is that data cleaning may induce strong dependence in this cleaned data matrix X hat. So what central limit theorem could we use for inference? Our answer will be to break a lot of dependence by using sample splitting, which is a classic idea, and implicit data cleaning, which is a new idea. So here's our algorithm on a slide. We'll split the data set into a training set and a test set. On the training set is where we'll do the data cleaning, where we'll learn an error invariable regression and an error invariable balancing weight. And then we'll bring those over to the test set, where we'll do causal parameter estimation and inference using the doubly robust estimating equation. Crucially, we clean the training covariates, but we do not clean the test covariates. And this is what I mean by implicit data cleaning. That'll break a lot of dependence. For proof of concept, in this paper, we'll opt for simplicity. We'll go for the easiest option in each step. For data cleaning, PCA. For regression, OLS. For the balancing weight, a modification of OLS, we call the BAL. And for the causal parameter, we use the doubly robust moment. Of course, the matrix completion literature gives us a broad menu for data cleaning. Machine learning gives us many types of nonparametric regressions, and there's a burgeoning literature about balancing weights. We hope that by solving the very simple case, we provide a template for how to think about the more complex procedures as well, though we're going to make the easiest options at each step. Let's see how our simple approach performs with measurement error. So instead of seeing the clean covariates X, we see the corrupted covariates Z. And here we've run the data generating process 1,000 times, computed 1,000 point estimates and 1,000 standard errors. Then we visualized 1,000 studentized point estimates. If the inferential theory was working, then this histogram should line up with a normal 0-1 density, and indeed it does. We can quantify this performance with coverage tables. And in the first table, we're ramping up the noise to signal ratio, 20, 60, 100% noise to signal ratio. For now, we'll do correct specification. So the rank of the DGP is 5, and we'll use 5 principal components. We can see how do our point estimates compare to the ground truth, which in the synthetic design is 2.2, and they seem pretty close. We also see that the standard errors adaptively increase in length as we drive up the level of noise. And interestingly, with a 100% noise to signal ratio, the appropriate standard error is only about 10% bigger. We know that the inferential theory is working because out of 1,000 confidence intervals, about 950 of them include the ground truth of 2.2. In the second table, we revisit this issue of tuning. So what if the rank is 5, but we use 5 or 7 or 10 principal components? The point estimates remain reasonable, the standard errors adaptively increase in length, and the coverage remains nominal. We receive, we get similar results with missing values, discretization, and differential privacy. And so the takeaway is that this very simple procedure seems to adapt to the type and the level of data corruption. Across all these different settings, we're just running the same code again and again. The third challenge is a theoretical challenge, and it has to do with the fact that the best rates of matrix completion, the rates at which we're recovering the clean matrix X from this matrix estimator X hat, these rates are not for recovering every entry of the matrix, but actually recovering matrix entries on average across rows and columns. So how is this even related to semiparametrics? And our answer, which is the focus of this section, is to build a framework to get from data cleaning all the way to data cleaning adjusted confidence intervals. So here's our theory on a slide. We place three main assumptions. First, that each row of measurement error is conditionally mean zero and sub-exponential. Second, that each row of missingness is conditionally sub-exponential. And third, that the matrix of the true covariates are approximately low rank. We've already seen this as reasonable in practice, and in the paper we further verify that it's reasonable in theory for nonlinear factor models. Then we prove consistency of the data cleaning, consistency of causal inference, Gaussian approximation, and validity of the confidence interval. So to interpret these results, we've gone all the way from a data cleaning guarantee and recycled those assumptions until we got to a data cleaning adjusted confidence interval. I'd like to emphasize that we're in a generalized setting with corrupted and INID data, and that our analysis requires both N and P to increase. So we're in this thought experiment of having access to many repeated measurements. We then use the many measurements to concentrate out the noise. En route to these results, we provide that theory of implicit data cleaning, that it's okay to clean the training covariates and to not clean the test covariates. In our main results, we provide that extension of double rate robustness we were looking for, whereby the rate of matrix completion is allowed to be slower than n to the minus a half, while the rate of causal inference is n to the minus a half. And in this way, it allows us to turn to the matrix completion literature in a general way. In the paper, we do something a little better. We do finite sample analysis, and that lets us think about the nonparametric case as well. So for causal functions like the conditional average treatment effect. So the takeaway of the theory section is that we do slow data cleaning, yet allow for fast causal inference. Let me end by doing a case study. So here we're going to use Otter, Dorn, and Hansen's important paper in the American Economic Review, where the data is from the census and it's at the commuting zone level. The original research question is, what is the effect of import competition on the US labor market? And our follow-up question will be, can we recover the same effects with synthetic corruption? In particular, with differential privacy calibrated to 2020 census levels. In this case study, the causal parameter of interest will be the partially linear IV parameter, which is different than the one we've been talking about, but it's still within our class. And here are our results. So in figure A, in red, we have the point estimate and the confidence interval from the original paper. And the original authors used two-stage least squares. Right next to it, in turquoise, we have our point estimate and confidence interval using clean data. And we see that we get essentially the same point estimate and a slightly smaller confidence interval. It's smaller for two reasons. First, 2SLS is inefficient, and what we're doing is efficient. And second, in the finite sample, the data is approximately low rank, and our estimator is exploiting that fact. As we move to the right, we introduce more and more measurement error, and we see the point estimates remain stable, and the standard errors adaptively increase in length. We get similar results with missing values, discretization, and differential privacy, where in the differential privacy exercise, we calibrate the Laplacian variance in a very specific way. So it's well known in the differential privacy literature that if you calibrate this variance to first, your tolerance for privacy loss as expressed in a Census Bureau memo, and second, the variation in the underlying microdata, then by adding Laplacian noise, we confer the type of privacy that we want to disrupt the hack that we're worried about. So it seems like there exist scenarios that are representative for economic research in which we can achieve both privacy at the individual level and precision at the population level. In other words, you can hide your cake and you need to. So in this work, we're motivated by the question of how to do causal inference with the 2020 US Census. Abstractly, we talk about learning a causal parameter from high dimensional corrupted data, but concretely, we're really interested in this question of, can we sometimes overcome the trade-off between privacy and precision? And sometimes can we not? In the paper, we propose new data cleaning adjusted confidence intervals. And at a high level, we try to bridge the matrix completion literature, which is very rich, and the semiparametrics literature, which is also very rich. In future work, we're trying to think about confounded noise and sample selection bias. I'd love to talk more, and here's my email address.
Thanks, Rahul. Very nice talk. Well, okay, we've just got another question in the Q&A. Anish was answering a few, but I guess I can ask you this one. It says, this sounds like missing this completely at random. However, your efficient estimator of the AT does not appear to leverage this. I guess this was a follow-up to a previous question.
Yeah, so it's
about missingness. Yeah.
Great question. So it's slightly more general than missing completely at random. So we allow for dependence of missingness within a row. And this was actually an innovation relative to previous work. This was motivated by the fact that in economic data, if you're missing my income, it's a lot more likely that you're also missing my spouse's income. So it's slightly more general than missing completely at random. It's still relatively benign missingness. As to thinking about how that should play out in the semiparametric efficiency, if this question, the person who asked this question could share some references, I'd love to read more about it and then have a better answer.
Great, thank you. There's actually two more questions. Since we have a few minutes, I'll ask them. What is your interpretation on stronger data corruption leads to stronger confidence on the effect?
So maybe I'll answer this one a little bit generally. In simulations, we tried out a lot of things. So I showed a very linear narrative, but we tried out kind of everything. And we found that when it comes to getting the most robust results, we want data to be approximately square. We found out that maybe there are a lot of estimators that could work well if you implement some of the techniques we're thinking about. And we haven't characterized all of them, but we just have a first pass. We found that the coverage is pretty stable. It's only when you get to scenarios where the data is very, very far away from being square and the data generating process is very, very hard that things start to break down. And they break down specifically in getting under coverage.
Great, thanks for that answer. Let me choose another one because we're getting a lot of questions. Do you have any thoughts about a scenario where the outcome is also noisy, as will often be the case in data protected with DP?
Absolutely. So in the paper, we also consider what happens with corrupted treatment D and corrupted outcome Y. When the outcome Y is corrupted in this way, in this kind of additive way, it's relatively harmless, right? That's kind of captured by the epsilon term. What if the outcome is missing? Well, as kind of an extension in one of the appendices, we think about attrition bias, where the outcome is selectively missing, and it's selectively missing with respect to these clean covariates. So there's attrition bias with respect to the clean covariates we don't get to see. And we kind of work out that extension in the appendix.
Great. Let's just end with one question. Hopefully it's short. So this is a question: how is the causal inference algorithm that you described better than baseline matching or propensity score matching?
So there are going to be many estimators that are semi-parametrically efficient. And I think something that's nice about this estimator and our analysis of it is that we have a finite sample analysis, even in the presence of corruption. And I think that from what I've seen, this is relatively new, but also very reassuring, because we want to know how things do in the finite sample, especially if we're thinking about analysis of aggregate units, when maybe there are only 100 or a few hundred or something like this. We want to have some guarantees even for that regime. So there are going to be a lot of estimators that are asymptotically equivalent. I think one nice property of this estimator is that, at least for now, we have finite sample analysis of it. That's a nice theoretical guarantee.
Great, thank you so much for answering those questions. I think now we will move on to Jiaqi's talk. Anish has also answered a few questions, and so Rahul, you're welcome to keep answering questions in the Q&A if there's interest. All right, Jiaqi, please.